Hello everyone. The traditional way to design controllers in robotics is doing it by hand. And what do I mean by doing it by hand? Well, first, what you do is you draw more or less what you want your robot to do. Usually we refer this as a finite state machine. I'm gonna come back to this term later on. But usually you start by a piece of paper and drawing what you need to do, what you want your robot to do. Then you start writing the code for it. You want to write the code that is going to make the robot do this. And finally, you put this code in the robot and then you test. If the robot does what you want, then that's good. If the robot doesn't do what you want, you need to change the code or you need to change the design. This process is good because we can identify the problems and we can have a fully grasp of what the robot is doing at any given time. However, this is a bit time consuming because you have to do all these steps. But what if we use tools to generate these controllers without the human intervention? Are these controllers gonna be better than the human designed ones, or are they gonna be worse? This is what we are gonna find out in today's lecture. It's gonna be human versus automatic design. In this case, we are gonna take a case of study already published by some authors called Automode. In the first part of the talk, I'm gonna very briefly mention how controllers are made by humans. This algorithm that was proposed by some authors. And finally, we are going to make the comparison and we are going to identify which one is better. Also, I'm going to very briefly talk a little bit about evolutionary swarm robotics. Well, let's start with the first part. Previous work. First, we need to discuss how do we design algorithms for swarm robotics. I have already mentioned this in the introduction. What people do most of the time is that they go straight to the piece of paper or straight to the block diagram and they draw the things that they want the robot to do. Once you're happy with it, then you make the code for it and then you test it. In my experience, the first step of drawing the diagram is really important. Because if you go directly through to the code, then you will have a messy code and you might forget key elements of the behaviors that you want in your robots. So it's important to draw these diagrams before going into coding. And this is the classic approach. Usually, when we're working with some robotics, there are two ways to make and to code these behaviors. The first one is what we refer as a bottom-up approach, where you design the controllers for each of one of your robots in your group, and then when the robots interact with each other, you have your behavior and you can achieve your task. So you start by the individuals and then you have your behavior. This is a most often used approach because it's easy to make because you work with the individuals themselves. Of course, it needs a lot of trial and error because one of the properties of some robotics is emergent behaviors, and sometimes it's hard to predict or hard to make the behaviors that we want from the interactions of the robots. But what if we do it in the other way? What if we do a top-down approach, where we have our task, our behavior, and we define our task, and then we code the robot. So we firstly think about it. We think about what kind of behavior do I want from my robots? And then you start coding this in order to achieve that behavior. Again, this is a bit more tricky because if you define a behavior, it's hard to identify what kind of interactions you want from your robots to achieve this. On the other, this is opposite as the previous approach where you just create emergent behaviors from designing these controllers for each robot. Not many people do this because it's complicated. For example, you try to imagine a behavior and then you write the code. I mentioned this before, but usually once you have decided your top-down approach or your bottom-up approach, the next step is to create the mathematical model, and then you test it in simulation, and then you deploy it in hardware. If in one of the stages you are not happy with it, you go back and you make changes. And this is the most classical approach. Right. Usually, in the hand design approach of the controllers, the human needs to think about what kind of controller he needs for his robot or her robot. Then he draws this flowchart or this finished state machine and puts it in the robot. If the robot works well, good. If not, you need to go to take one step behind and make changes to your design. So this is a classical approach. 3 steps. You think about it, you draw it, you code it, and you test it. Okay? Good. As I was saying, the feedback is important because in this way you can make changes and optimize your controller. The advantages of hand-designed controllers is that you can see the progress. If the controller is not perfect, you can make changes and you can track these changes and you can identify what's the problem or what are the things that you're getting. Also, if you see your robot performing or your group of robots, you clearly understand what's going on because you wrote the code for it and you can identify bugs easily. However, there are 2 main downsides. The first one is that it takes a long time. Like I was saying, it's an iterative process. So you design your controller, you test it. If it doesn't work, go back, change it, go on and on. This is a lot of trial and error, and it can take a long time. Especially when you're testing your robot in hardware. And the second downside is a bias introduction. We humans, even if we don't want it, we have some bias in all decisions. So we might introduce this bias in our robots, and this bias could be bad. Whereas a machine, if the machine designs this controller, the machine will not have any bias. Okay, we have seen the advantages and the disadvantages. But the question here is, can we automate the design process? And the answer is yes. There are many different methods, and I'm just going to mention one here, and then we can see how this can be achieved. In the automated controller design, you have a computer instead of the human, and the computer decides what kind of controller you need. Most of the time, people use neural networks for this kind of controllers. In this lecture, I'm not gonna go into into much detail about neural networks. You're gonna have a module about this later on. But my point is that the computer changes the controller, in this case a neural network, and then the computer tries this. If the computer is happy, that's great, isn't it? But if the computer is not happy, well, you need to change the parameters on your controller. You need to change the structure of your neural network. And this process repeats over and over and over and over. However, this is done by the PC, and the human doesn't need to take any decisions. It doesn't need to go to the piece of paper, to the flow diagram. Everything is done by the machine. What are the advantages? Like I was saying, it takes way less time because the machine is gonna do it quickly. It's gonna try multiple different things. And if you are using a cluster or multiple PCs, you can run multiple experiments at the same time and test it and change parameters and so on. The PC is not gonna introduce bias. It's gonna always aim for the perfection. It's gonna try to approach the perfection, the perfect behavior. However, a downside is that there are two. The first one is a complex controller. Neural networks are great. They're really useful. You can train them to do for robots to make many different tasks, but unfortunately they are complex. For example, if one of our behaviors is not working, or if we detect a bug, it's really hard to identify what went wrong in a neural network. Why? Because you have many nodes, you have many parameters, and you need to check each parameter. In that case, for example, if you want to create a safe robot, it's really hard with neural networks because you need to test each tested scenario where the neural network does what you want. This is not the case with the human design because you understand what's going on. And the last one, the reality gap. If you use an automatic design, the PC or the machine is going to exploit whatever it wants or whatever it needs to achieve the behavior. It can exploit simulation artifacts. For example, if your simulator is not accurate and the friction is not accurate to reality, it might exploit that, and it will create controllers that work very well with this different friction. But once you test it in hardware, this is not gonna be the case. Again, reality gap. Always remember about this. Okay, let's see one of the examples of automatic design. This is called Automove. But before we go into any more details, I would like to talk to you about state machines. State machines are commonly used in robotics. Usually, in a nutshell, a state machine is a diagram where you put all the blocks that you want your robot to do, you connect those blocks, and then you code this. It's a really nice way to create controllers because it's very modular. You can encapsulate each behavior in a different state, and you connect these states by actions. So, if you're not happy with your behavior, you might need to replace one behavior by another. In a nutshell, this is a state machine, but let's dive into more detail. It's like Lego blocks. Well, you can try different Lego blocks until you're happy with the design. I like this analogy because it represents perfectly the advantages of state machines. Okay, imagine in state machines you have what we refer as modules. Each module represents a different state. Also, like the state machines have actions. These represent transitions between one state to a second state. And then you can create different complicated diagrams like this one, where one action can trigger another state and you go back to that state and so on, and you can connect it in different ways. This is one example. Or now, and now I would like to create a state machine. Let's imagine that we want to create one. And we're going to use the epoch robot. We have seen before what are the features of this robot. It has infrared sensors, it has two wheels, it has range and bearing. The task that we want to achieve is that we want to collect as many robots as possible in one or the other circles. For this, the robots can detect the color of the surface. So the question is, if we have to use a finished state machine, how do we make this? Well, we start dividing our task into behaviors and actions. For example, we are going to need exploration behavior where the robot just wanders around searching for one of these black spots. We need a stop behavior, which represents that the robot needs to stop at the black spot, because remember, we want to aggregate many robots in single black spots. You could have phototaxis, for example, that robots feel attracted to other robots or to a beacon. Anti-phototaxis is when you feel repelled by the other robots or a beacon. You can have attraction and you can have repulsion, which work very similar. We are going to need some actions because we need to make these transitions from one behavior to another behavior, to one state to a second state. In this case, one action could be, I have found a black floor. What should I do next? I'm in the gray floor. What should I do next? I'm in the white floor. What should I do next? How many neighbors I have? How many neighbors are lacking? And so on. So, okay, how we do this? The way that we achieve this, what the auto before I explain the final state machine, what auto mode does is very interesting. It tries different combinations of behaviors, and then it tries different combination of actions. For example, the one that we are seeing here could be one result, or this could be the next one, or this could be another one. And what auto mode is evaluates each of these state machines and selects the best one. So that's what basic auto mode does. Okay? You try different combinations of finished state machines until you find the one that it works. This is made autonomous. Here, in this slide, what I'm showing is that number represents the fitness or the performance of that state machine. In this case, the bottom right corner, according to the auto mode algorithm, was the best one. And this is the algorithm that you're gonna test in your robots and that you're gonna code. Again, this is done autonomously. Automode tries each of these state machines until it's happy with the results. As I was saying before, just a brief summary about it. The controllers are made of predefined modules and conditions. The advantage of using finite-state machines and modules like this is like there can be changed easily by humans and we can understand what's going on. Automod generates the best controller by switching these elements, the actions and the states, and in theory, these controllers should work for any robot as long as the robot has the components the necessary components. For example, we need a sensor that is pointing downwards. If your robot has that sensor, you could use this finite state machine generated. And yeah, for the example that I was mentioning before, this is the result. Basically, all what you do is to move towards a group of robots. In this case, that's the abstraction state. If you found a black floor, you stop for a little while. That's very important. For a little while, you're gonna be there. Then, if you start moving, and if you detect the gray floor, you do attraction because you are outside of the black spot. So you need to approach other robots. But if you continue being in the black floor, you just move inside the black floor and stop, and so on and so on. In this way, we can aggregate the robots. And this algorithm, this finite state machine, was the best one generated with Automod by the researchers. Okay, that's great and everything, but which one is best? Is it better to a human doing it, or is it better to have a machine doing it? Well, we're gonna find out. In this case, what in the experiments carried by the researchers, by the way, the list of papers is at the end, and you can refer to that. They use different methods. On constrained human, it means that you ask a person to make a controller, and that's it. He has all the freedom in the world to make this controller. A constrained human is you give the states and the actions, and the human has to design a controller from this. Evostick, it means that you evolve a neural network controller, not a finite state machine. Automode with F-rays, you use a finite state machine. And Automode with iterative F-rays is it's an enhancement about it. So yeah, I'm explaining everything here again, but this time with diagrams to make it clearer. In the constrained human, it's a black box. It's up to the human how to make the controller. If the human wants to draw a diagram, a finite state machine, that's fine. If the human wants to go directly to coding, that's fine. The constrained human, you just give it the actions and the states, and the human needs to decide how the controller is gonna be made. In the neural network one, the PC tunes the neural network, changes the weights in order to make the robot do something. And EvoStick, instead of a neural network, is gonna be a finite state machine, and the PC is gonna decide how the states which states to use, and how these are gonna be connected with actions. Okay, that's great. So, which one is the best? Which one do you think is gonna be the best one? Remember about the advantages and disadvantages of it. So let's see. In this case, they are comparing the four that I just mentioned in their first paper, and they found that the constraint is the best one. If you give enough tools to people, they can create really good controllers. In second place is the vanilla one, which uses the machine uses states and actions to create controllers. Just, I would like to mention something quickly. Take it with a grain of salt, because in the vanilla one, we give prior information to the machine, which means we more or less know what we need, and the machine knows what to use. Whereas in the EvoStick, the machine has zero knowledge about it and starts from scratch. So yeah, just take it with a grain of salt. And the unconstrained human has the worst performance. Again, I mentioned this as an advice at the very beginning of this lecture. From these results, we can see that, if possible, when you're writing controllers, first draw the diagram before going directly to code, because as you can see, if you have a diagram, you can create better controllers than without it. So yeah. But the authors didn't give up. They said, okay, we feel like we can do something better. So they did. They created a better version of vanilla called chocolate, and it did beat the constraint human. It had better parameters, it was better optimized. Alright, so machines can do a really good work. We saw that there are a few disadvantages. But something that I would like to very quickly mention, since my background right now is about evolutionary robotics, another automated way to generate controllers is by using evolutionary swarm robotics. Most likely, someone else is gonna explain you about some evolutionary swarm robotics, but I'm just gonna give you a little bit more detail about how this works, but very briefly in a nutshell. Okay, basically, what you have on the left is a very simple neural network, and what you do in evolutionary robotics is that you translate the neural networks to what we refer as genomes. In this case, what you translate, it depends. There is a wide variety about how you can do it, but in most research, you took the weights of the neural network and you put it in a string. In this case, we have four parameters, A, B, C, and D, and that's gonna be our genome, okay? And that's what we are gonna change, and that's what the PC is gonna automatically find out and optimize. In this case, in traditional evolutionary robotics, you have a population of genomes, which is the first row, and you evaluate each of those genomes. Each genome has different values, and then you select the best ones, and it depends how you do it. There are many different ways to do it, and I could spend hours talking about it. But you can select those two best ones and make copies of it, exact copies, because we choose the elite. We don't want to lose these good genomes. But what about the other three genomes in our population? Well, we make copies of the best ones, but now we make small changes to each genome. This is referred as mutation. When we make tiny changes to the fitness, to the weights of the neural network. These small changes could be good or they can be bad. It's worth to take the risk, because if they can be better, then we found a better genome. And this process repeats on and on and on, generation after generation, where a generation is a population of each genomes. But okay, that's great, that's good for a single robot. Wow, but what about the swarm robotics? You have many robots. How can you translate this into evolutionary robotics? And that's what we are going to see in the next couple slides. There are two traditional ways to achieve this. In the first one, it's referred as homogeneous, and in this case, what you do is that you have a single genome or a single controller for all of your robots in your experiment in some robotics. So basically what you do is you take a copy of the genome and you put it in all the robots. And all the robots are gonna share the same genome. What does this mean? Well, it means that all the robots are gonna behave exactly the same. This is great most of the time. There are a few cases which is not very useful. When are these cases? These cases is when the task is divided into multiple different tasks. Therefore, if all the robots share the same genome, it's gonna be really hard to evolve a robot that can do multiple different tasks. It is possible, but it's hard. And it's gonna take a long time. That's a disadvantage. But what about the advantages? Well, that this method, the homogeneous one, it's easy to optimize because you have a single genome and you just have to optimize that. That's quite quickly and simple. Okay, and this is the heterogeneous one. And the heterogeneous one, it works in a very interesting way. Each robot has a different component of a genome, not a different genome, a component. Okay, what do I mean by this? It means that you have a single genome of, in this case, is 16 characters, and you divide that genome into multiple parts. The first 4 characters are going to represent one robot, the next 4 another robot, the next 4 a different robot, and the last 4 a different robot. In these ways, the evolutionary algorithm can optimize this single genome that represents multiple different robots. What are the advantages of this? I just mentioned it in the previous slide. If your task has multiple different subtasks, you can optimize specific robots to perform different tasks, which can be really useful. So basically that's it. You have these 2 methods and you can evolve it. It was a very briefly introduction to evolutionary swarm robotics. If you want more information, you can get in touch with me and we can discuss it further. Now, I'm gonna mention a few examples in evolutionary robotics. This graph represents a robot the group of robots moving to a light and getting away from it. And it's oscillating. When the light is on, they approach. When the light is off, they go back. And what they found is that it works very well for the homogeneous controller. All the robots work well. And this makes sense because basically in this task you don't need robots interacting with each other, which basically it's a very simple task. But what about a more complex task? In this case, this was very interesting. The robots had to move together towards a common target, a directed locomotion. And the robots had traction sensors, so they felt whenever another robot was moving. And this is really useful because with this information, that robot can decide when or not to move. And the authors were able to evolve behaviors for this specific task. And the last one, and that I found the most interesting one, is that the robots are assembled to each other, creating this structure. And the robots have to navigate the environment, but it was on a table, and that table didn't have walls. So if a robot reached an edge, the robot had to take a decision to avoid that edge, so they don't put at risk all the robots. And they did it. This works well. Whenever a robot is at the edge, it moves to other direction. The other robots feel the traction and they change direction. And these three tasks were done and optimized by a machine without the human intervention deciding which algorithm or which controller was best. So yeah, this is just a complementary information about human design versus autonomous design, and there are many different algorithms to achieve this. To summarize, what we saw mainly here is that you use finite state machines to create the controllers, and you can optimize this. And the advantages is that you understand what's going on without getting into neural networks, which is a little bit more complicated. So automotive, it's great because of that, because it optimizes finite state machines. The main disadvantage of the automode with finite state machines is that you need prior knowledge, you need states, you need actions. So you need to feed this information to it. What if you are doing a very complicated task and you as a human don't have this knowledge? This might not work, and that's the main downside of this. The first part, we talk about previous work, how people have done, have made these controllers for robots in some robotics, the automode approach, and human versus automatic design, where automatic design can be better than human design applied when applied correctly. And it's better to optimize state machines than neural networks if possible, if you have the prior knowledge. And that's all for me. Here are a list of reading that you can find about the auto mode, then a little bit of more about information about evolutionary some robotics that I found really interesting. And finally, some blog posts that I wrote and that can be complementary to this lecture. Thank you very much and see you next time.